Alright, this video is all about one thing, and we're going to answer the question, or basically the idea, what is a mathematical limit? So I want to start off with a pretty nice concrete question, and this is about a car racing down a drag strip. So this is actual data here taken from Joliet. So someone drove a Corvette down a raceway, and what you end up with is a little time slip which shows the time that has elapsed and then also how far the driver has traveled. You can see the distances in both feet and miles, so what we can do is to convert that at a later time. So a common thing that people will ask about to measure the performance of a car is how long did it take for the car to reach 60 miles an hour. So how long did it take to accelerate from 0 to 60 miles an hour? So this is a pretty common question. I'm just going to write down a couple of things here. So 60 miles per hour. And because the distance here is in feet and miles, it would probably be easier to convert these to feet. So you can do a very quick calculation, dimensional analysis, and 88 feet per second is the same as 60 miles an hour. So in a nutshell, what we're doing is, based on this data, we're going to try to figure out how long did it take the Corvette to reach 88 feet per second. So one of the basic things we can do is, because we have data that is spaced out, we have discrete data, is we can plot these points, and typically we'll do time on the x-axis and distance on the y, and then we can take a look at the trend, right, and really see what's happening here. So here's a rough little graph of what the data looks like. And so this axis here, this is time, and up here we have distance. So the time here is measured in seconds, and the distance is in feet. And you can see we have 1, 2, 3, 4, 5, 6 data points, right? And they're really corresponding to the differences that we have here. So we have those values plotted, and because the trend is pretty visible, what we can do is to connect them with a nice smooth curve. So I'm going to try to do that. It doesn't have to be perfect, right, but it will look something like that. And so there are tools you can use in statistics to get the actual curve, right, that mimics this trend. And I'm going to call this curve S of t. So t stands for time, and d here is standing for distance. And so what we're going to try to do is to pin down the answer to this question, right? How long or at what time moment did this person actually reach 88 feet per second? So there are a couple of ways that you can think about doing this, right? And that is to look at some of the data and to start doing some pretty simple calculations. So let's look at a couple of different things here. So if you want to look at the first 60 feet, for example, what we can do is to borrow one of our old formulas from algebra. So this one will come to mind, right? So distance equals rate times time. And so this person driving the Corvette is asking a question about the rate. So if you rearrange this, rate is distance over time, right? So it's the distance traveled over the time that has elapsed, right? The time that has gone by. And if you look at this carefully, the distance is here, right? It's measured on the y-axis, and time is here, measured on the x. So we're doing a simple division, right? Distance divided by time. Change in y over change in x. This corresponds to a very simple slope, right? Something that we know from algebra. So what we can do is to compute the average velocity on certain intervals, right? Looking at some of this data there. So if you want to look at the first 60 feet, right, we could do the change in distance over the time that has elapsed, about 1.3 seconds. And you will get the driver's average speed on that window. So what I'll do here is I'll just kind of hold this one up, right? So if you use the first 60 feet, so we're using 2.063 and 0.734, this is the difference in the distance, right, corresponding here, and the difference in the times. And you can see the average velocity here is 45 feet per second. So over the first about 1.3 seconds, the driver is moving at an average rate of about 45 feet per second. So if we highlight these two data points, and I'll do this right on the graph, right, so I'll try to find those points. that would be this point here. I'll make them a little bit bigger, and that one there. So if we think about the rate as being a slope, right, change in y over change in x, what we can do is to draw a little line that connects these 2 points. And so I'll try to do this here as best as I can. Right, so I'll take these 2 points and connect them with a line, right? So when we look at the slope of that line, right, the slope of this line is going to correspond, right, to this average velocity, right, the slope being 45 feet per second. Okay, so this line is a special thing in mathematics. We call this line a secant line. It passes through 2 distinct points on a curve. So I'm just going to write down that idea. This here we call a secant line. Okay, and this is giving us the average speed of the Corvette over the first 60 feet. So something you'll notice that will change is that if you move to a different interval, right, you're going to get a different value. So if you now look between, say, 60 feet and 330 feet, that means you're going to be using different data, and as a result, you expect a different speed. Okay, so to show you the quick calculation here, so using the 2.063 and the 5.387, you'll notice that the average speed has changed, right? This is 81 feet per second. So the same type of thing, right? What we're going to do here is to grab the 2 points, right? This is around where the 2 seconds is and around the 5.3. So you grab those 2 points and you repeat the process. So I'm going to draw a secant line here to the curve. So this is what this one looks like. And you can definitely tell the slope of the second line, right, is steeper than the slope of the first. And that's something that you can see in the 2 calculations, right? The first calculation was near 45, and now we're up to 81. So the average velocity that we're calculating here is corresponding to the steepness, right, that we see in the graph. Okay, so the bad news about all this is pretty easy to calculate, but at the same time, none of it is really going to answer the question here, right? And the question here is, at what time moment or how long does it take to reach 88 feet per second? So I'm going to switch gears here, and we'll talk about the basic idea, right, what we're trying to do. So this is a more general setting here. So I'm going to use the same letters, time and distance, right? And so you might have a curve, right, something that looks like this, and I believe we called it S of t, represents the position of the Corvette. And so what we just saw just playing around is we grabbed 2 time moments, right, and we found the corresponding location on the curve. And if you connect these 2 points with a straight line, right, we get this secant line idea. Okay, and this corresponds to the average speed. So what we're going to try to do here to talk about an actual instantaneous velocity is we're going to hold one of these points fixed, right, this one on the left, and we're going to take the point on the right and slowly move it towards the first point. So we're going to bring this a little bit closer here, okay, and we find a new location here. And so what you end up with is almost like an updated secant line, okay? So we're going to connect these 2 points here, and you'll notice the steepness of the line has slightly changed. And we repeat that process. We're going to let the second point move even closer to the first one right here. So I'll do this one more time. So you end up with something like that. And then eventually the basic idea is we're going to let the second point get very, very close to the first, almost to the point that the 2 points coincide, right? So the 2 points become one, and then you get this idea of a tangent line, okay? And a tangent line is a line that just kisses the curve at 1 point, so it really just touches it at that 1 point. And so in the limiting sense, right, if you look at a bunch of these secant lines, but you're letting the interval shrink, a secant line becomes what we call mathematically a tangent line. Okay, and the tangent line here, the slope here corresponds to a single reading of velocity, right? So the window here becomes so small that it is more or less equivalent to looking down at your speedometer and just getting a single reading. And that is something that can correspond to the 88 feet per second or the 60 miles per hour, right? The main thing that we're after. All right, so if we just bring this problem back, I just want to show you a couple of things, right? So bring the Corvette problem back, and the person is simply saying, you know, how long, at what point did I reach that 60 miles an hour or that 88 feet per second? In theory, what you could do is to play around with these different quotients, right? Distance over time. And it turns out that the solution to the problem is very close to 4 seconds. It's around 4.17 seconds, right? Depending on the particular curve that you use. And so one way I want to illustrate this so you can see the essence of the idea, right, is look at some data here that corresponds to what we did graphically. Okay, so what we're doing here is we're going to look at an interval of time, right, just like we saw before, and then we're going to calculate that distance over time, that simple calculation, and you'll notice you get these average velocities. So if you calculate from 4.17 to 7 seconds, that's a pretty wide window of time. And you can see the average speed of the Corvette was around 105 feet per second. And so what we're doing, just like what we did graphically, is we're going to keep the first point fixed, but we're going to let the second point get closer and closer to that 4.17. And so as you recalculate the average velocity here, you'll notice there is a change in the numbers on the right-hand side, but it's a moderate change, right? So you can see some regularity occurring on the right-hand side. And then finally at the very end, 4.17 to 4.19 seconds, we're really, really close to that 88 feet per second. So we could say really somewhere in this window, a very, very small window of time, right? This is where you achieve that 88 feet per second. And this really is the essence of the mathematical idea of a limit, right? So as we approach a single value, and in this case, on the left-hand side, that single value would be 4.17 seconds. As we get closer and closer to that value, then it looks like we're approaching a different corresponding value, right? Something that corresponds to it. And in this case, we would say the limit is 88 feet per second, and that happens when time is very, very close to 4.17 seconds. Right? So the big thing here, right, just to summarize everything that we talked about, we're trying to learn about the idea of a limit. But the person driving this car was basically asking that simple question, when did I hit 60 miles an hour, right? So it's really this question here. At what time moment is the instantaneous rate of change 88 feet per second, right? So at what moment in time did this driver hit 60 miles an hour? And so what we're finding out geometrically, right, when we look at this mathematically and in a graph, there's another question that appears to be different, right? And this question is, when is the slope of the tangent line 88 feet per second? And what we have found out in this little video is that these questions actually have the same answer, right? So at what time moment is the instantaneous rate of change 88 feet per second? It's around 4.2 seconds, right? 4.17. And when is the slope of the tangent line, when does that measure to be 88 feet per second? That's the same thing. Right? And that's what we're seeing from this, is that these are two ways of formulating the exact same question.